we should hopefully. Okay. We've already discussed that our thermochemical equations, okay, all this means is now we're looking at the thermo portion. We're looking at the heat being released or absorbed. So we've been looking at that. We looked at that actually the first day of class. Okay, and so now we know that correctly to show the full reaction, including that heat value or delta H, okay, so that's our enthalpy value. Okay, and technically, I have it both ways because you see it both ways in the book. Okay, but technically delta H is kilojoules or joules per mole, right? But it just is understood that you know it's per mole. Okay, so if you want to write in mole there, feel free if that helps you. Okay, so now we're going to look at the ratios. So just like in Chem 1, we said we have a 1:2 or we have a 1:3 ratio looking at the different reactants in the products. Okay, but we're going to do one thing that is a little bit different. Okay, so if we look here, if we were to read out this equation, we would say that for every 1 mole of pentane, that's C5H12, okay, reacts with 8 moles of oxygen, okay, to produce 5 moles of CO2, 6 moles of water, and it releases 3,523 kilojoules per mole of heat. Okay, so that's kind of technically how we would say it. Okay, so if we look at the coefficients, just like we know, everybody hopefully remembers these numbers out front, right? These numbers in front of the compounds are our coefficients. Okay, we actually interpret these as the number of moles. Okay, but we also consider this whole reaction to be out of moles of reactions. Okay, so that don't make much sense right now, but hopefully it will by the end. Okay, so what we would say here is that all of this that I just described, so the whole equation, is out of 1 mole of reaction. Okay? So if we want to write out unit factors, so I want you to take just a second and think about, okay, our unit factor is basically, so one that you all probably would do right off would be 1 mole pentane over 8 moles oxygen. Okay, that would be a unit factor. Okay, so think about some that you would already know. And then we're going to throw in a few using this 1 mole of reactions to kind of show you what I'm talking about there. Okay, so basically write out your ratios that you have. So if we were comparing, let's say, 8 moles of O2, we were going to convert to water, we'd say there's 8 moles of oxygen for every 6 moles of water. So that's one. You could use the pentane and 5 moles of CO2. All of those are just the ratios that we have between the reactants and the products. So you could do 1 to 8. You've got an 8 to 6. There's lots of different scenarios there. Okay, but kind of our new unit factor here is that we have, we'll start with C5H12. We have 1 mole. C5H12 out of the whole entire reaction for every 1 mole, and I abbreviate reactions as RXN. And so this is our new ratio. This whole equation was out of 1 mole of reactions. Okay, and so we could go through and we could do this for all of them. So we have 8 moles O2 out of 1 mole Yeah, we're just looking at separate unit factors. Yeah, we're not doing any of the equations with them right now. Okay, the reason that we do this, we could keep going. So we could do 5 moles CO2 for every 1 mole of reaction. Okay, the whole equation is always out of 1 mole of reaction. So that's never going to change. So when we start doing our problems and working problems, it's always 1 mole of reactions. Okay, so that doesn't change. Okay, the numbers that can change are your reactants or your products here, the compounds that, they could be depending on the ratio. So we have an 8 here. And if we wanted to compare water, we would have 6 moles of H2O for every 1 mole of reaction. Okay, the reason that we need this is because we need a relationship, because we know the relationship here. These are compounds, and they're all added up on the periodic table, their molecular weights, and so we compare them that way. Okay, but for this heat value, okay, we're going to start using it in equations, and we need something that's a common relationship. Okay, so technically, what we say here is that 3,523 kilojoules per mole of reaction. And like I said, sometimes the book will write this out, sometimes it won't. It's just understood that you know that it's out of moles of the reaction, okay, because it's placed into a reaction, so it's moles of reaction. Okay, so now I'm going to show you how to use this. So I know it's kind of a weird concept. What's the point of this 1 mole reaction? Okay, and the point is that we are going to be able to determine heat values or come up with delta H values based on information that we're given, okay, because we have a relationship of the energy, okay, or the heat per mole of reaction. Okay, so let me show this real quick. The best way to show it is to demonstrate it. Bear with me, we're going to come back to that. Okay, so here's an example. Okay, we're given the mass of dimethyl ether. Okay, dimethyl ether is this compound right here, one of our reactants. Okay. And it said that it's burned at constant pressure, and it tells us that 82.5 kilojoules of heat is given off. It's giving us heat, which that means our units are what? Just kilojoules or joules, right? Okay, and we want to find delta H. Okay, so we talked about this last Wednesday. Okay, delta H is joules per mole or kilojoules per mole. Heat is just joules. Okay, so we want to find delta H. So that means we need to find or use the joules, really, that were given here, or kilojoules in this example. And what do we need to find? Okay, so we're going to use our balanced equation, and we're going to find the delta H. Okay, so there's really, your book kind of complicates it a little bit. There's really more than one way to do this. But to me, the easiest thing to do is to recognize that you're given the kilojoules. Okay, so we need the kilojoules per mole. So the first thing I'm going to do is I'm going to take my grams and I'm going to convert to moles, right? Okay, so if we have 2.61, okay, just for sake of practice, to be sure you didn't forget this from last semester, I'm going to have you guys add up the molecular weight of the dimethyl ether. It's a common mistake just because I assume that you remember, but sometimes that's not the case. Okay, and whenever we use the periodic table and we add up the molecular weight, it's always out of 1 mole, right? Okay, so that's going to go up top. Everybody agree with 46.0 or 46.08 as the molecular weight? Okay. I just had 46.0, so it just depends on the periodic table. You'll all be given the same periodic table, so you can just use those numbers. Okay, so here, this is nothing different than what you did last semester. Okay, so now we are in moles of the dimethyl ether. Okay, but for delta H, remember we're looking at the heat being transferred in or out. Okay, we need kilojoules, okay, which we've got kilojoules, right? We've got a heat value there. We've got 82.5. Okay, but now technically we just looked at moles of reaction, right? So we've got to relate this to our equation. Okay, and so we have to add in one more step here. And we're going to show it even though it's going to be a 1-to-1, but it won't always be a 1-to-1. Okay, so for 1 mole, our coefficient's understood to be 1. So this is where we look at, this is our ratio. This is where we look at the equation. So for every 1 mole, we have 1 mole of reactants, right, of reactions. For us to relate heat and the coefficients, or to relate to our reactants or our products, we have to go to moles of reactions. Okay, had this coefficient been a 2 or a 3 or whatever, anything other than 1, it's going to change your answer. So if you forget this step, then you're going to get the wrong answer. Okay, so here it's just times 1, so it doesn't affect us. But okay, so we end up getting, let's see, 0.0567 mole reaction. Okay, the reason for this, think about it. We're looking for kilojoules per mole or per mole of reaction. If we just plugged in moles here, we're plugging in moles of dimethyl ether. Okay, we're not plugging in moles for the reaction. Okay, so that's why you can't plug that number in. Okay, so now we have moles. So if we look at, for delta H, we need joules or kilojoules per mole. Okay, we're given kilojoules, so why not just keep it that way? Okay, and so if we take, I have to erase some of this real quick. Okay, so if we take our 82.5 kilojoules, divide it by the moles that we just found. Okay, I think I got about, okay, and you're going to round, so technically at 1454, but if you round to 3 significant digits, you get 1450. Kilojoules per mole reaction. Okay, so there's really 2 different types of equations we're going to be doing. So this is one. Okay, so you're given the heat value. So all you do is use it in the end with your delta H. Okay, and you convert from grams to moles just like you did last semester. And then you add in that one step where we have to look at the moles of reaction. So that's why we did the unit factors at the very beginning, because that's where we plug them in, right here at the end. Okay? Okay, any questions on this one? Okay, so this is the second type of thermochemical equation that we can be asked to work a problem with. Okay, so read through it real quick first before we get started with it. See what you see. I have it bolded, but what's the difference between the two? Between the one we just did and this one? Okay, so Emily just said it looks like we're looking for heat this time. So we're looking for heat, which she said means our units are just going to be joules or kilojoules. Okay. Versus what were we looking for in the previous problem? Delta H, or you had to find moles. Okay. So what else are we given here? Where are we going to start? What values could we start with? Okay, we'll talk about this here in a minute. So the temperature, this is standard temperature and pressure. So it's just given just so you know, because it would change if it wasn't. So not worried about it right now. Okay. This is given to us also. So we're given delta H. We're not finding it this time. Okay. All right, what do you think would be a good place to start? Okay, so we're looking for the heat released by 24.2 grams of aluminum, okay, for the reaction. Okay, so a good place to start, Tina said, would be start with our grams. Okay, what's the formula weight for aluminum? Pretty easy. Just look at the, so basically 27. Okay. Always out of 1 mole. Okay. Okay, so we've gone to moles of aluminum, okay, but we're trying to relate our heat with the molecular formulas, or with our compounds. Okay. So what are we going to have to do again here in this step? Okay, so we're going to set up our unit factor, or put in our ratio of aluminum, the number of aluminum moles, in 1 mole of reactions, right? Okay, so how many moles do we have? Aluminum, exactly. So this time we have a 4, where we had a 1 previously. Okay, and this is always out of 1 mole reaction. Okay, so the first 3 steps, or first 2, sorry, just like we did earlier. Okay, and then instead of breaking it into 2 parts, now we're set up. We have mole of reaction. Okay, we also have a mole of reaction term right here, right? So we can just plug this number in for a final step. Okay. And then we will do like so. So in 1 mole of reaction, I'm getting that from right here. And we have so this is new. We've got this equation set up. You know, last semester you went from grams to moles, moles to grams, or took molarity to moles, or whatnot. Okay, now we're going from grams to moles of reaction. So now that we have a common relationship between our delta H, okay, or with our delta H. So moles of reaction cancel. Okay, so it's just like we've learned previously. You want your units to cancel until you're left with the final unit that you're looking for on top. Okay, so we multiply everything on the top, Multiply everything on the bottom, divide the denominator into the numerator. And so, and in this case, so about 751 kilojoules of heat is released. Okay, so that negative doesn't mean negative. You can't have negative heat, okay? It just means that it released 751. Okay, so that just tells you that we have an exothermic reaction. Everybody got this? You got it, Tina? Okay. Okay, let me go back to the ones we missed here. Okay, there's two ways to write out a thermochemical equation. We actually just saw both ways. Okay, you will sometimes see the value placed into the equation. So it would say, so here this is exothermic, so it would have plus 3,523 kilojoules. So that's what we just saw over here. Okay, see how it's added in there? And you just know it's exothermic because it's on the product side. Okay, you'll also see it written like this, where it just tells you delta H, and it just puts that negative sign there. Okay, it's the exact same. Exactly. So if delta H is negative, it's going to be exothermic reaction. So if you want to look at it this way, you can, or if you want to add in. Some students, because that negative's there, they put minus 352. Okay, you can't have a negative in your equation. Okay, it's just added to the product side. Okay, so this is the exact same equation as the previous slide. Yep. Endothermic, okay, that number right there is going to be positive. Okay, all that means is that that value should be added in over here. Okay, so there's just two different ways of looking at it. Okay, example 15.2. Hopefully you guys have your printouts, but if not, we'll go back. Okay, it wants you to write the thermochemical equation. Okay, when it's thermochemical, it's not just your typical equation. Hopefully everybody sees that by this point. Okay, you've got to add in that delta H value. Okay, so if we go back, this is what we did on last Wednesday. If we go back for this example, oops. Okay, we found delta H. This is 15.2. So we found delta H to be 56.8 kilojoules per mole. Okay? So now if we go back and look at what our reactants and our products were, okay, so there they are. They're also right here. Okay? So you can write it both ways. So write your thermochemical equation. We found delta H to be this. Okay, so I want you to write it both ways. Okay? And it tells you right here that heat is being released. So what does that tell you? Endo or exo? Exo. Okay, so write the chemical equation both ways. this is one way. Up 56.8. I was making my pen there for a second. A little bit better. Okay, so there's one way. So we add the delta H value into the equation. Okay, and the other way it would be written would be out to the side, so I don't really have any room there, but just would have your equation there without the value, and then it would say delta H equals, not liking me walking around here. Delta H equals that would kind of be out to the side, and it would have that negative sign just telling you that it's exothermic. Okay? Okay, here's a few more terms, just if you come across or use these in class or in lab. The main reason that I'm showing this is because at the end of last semester, we learned the standard temperature and pressure for gases, okay, and the thermochemical standard state of a substance when we're talking about enthalpy in its pure form. Okay, it's not to be confused with STP. Okay, so if you look here, does anybody remember what standard temperature and pressure, what those values were? Okay, 1 atm. Okay, so that matches up here. Okay. Okay, and 273 Kelvin. Okay, so look up here. What's this? 298. Okay, so it's different. So it's not 273. And it's 25 degrees C. Okay, so those two values are your standard temperature and pressure when we're talking about the enthalpies and looking at the energy of reactions. Also, if it's talking about the standard state of a gas, it considers it at 1, so that's kind of repetitive there. Okay, but for a solution at standard state, it considers it to be 1 molar. Okay, so that's just kind of a value, kind of easy to remember. But so if you see this right here, kind of a subknot, what do we call that? Okay, this superscript at 0 just indicates that the reaction is at standard pressure and temperature. Okay, so it's at 1 atm and 25 degrees C. Okay, so if you see that, that's what that means. Okay, now we're going to throw in another delta H, or another term. So right now we've got Q, we've got, for heat, we've got delta H for enthalpy. So here's our heat value. Okay, I'm going to throw in one more. This is called delta HF. Okay, it's actually not called that, that's its symbol. It's called the molar enthalpy, standard molar enthalpy, for the heat of formation. Okay, you want to know both of those terms, but the one that I use because it just makes more sense is the heat of formation, because that's what we're looking at. We're looking at how much heat does it require to be transferred in or out of the system for us to produce this product, or for us to produce a substance. Okay, and so the symbol for heat of formation is this delta HF. So that's why I think of F formation, kind of makes more sense. Okay, you see here you've got that subknot. That just means standard temperature and pressure. Okay, so if we look at the heat of formation for magnesium chloride, okay, it was an exothermic reaction, so 641.8 kilojoules per mole were released. Okay, So it took this much heat here for magnesium and the chlorine to react to produce the product. We're looking at the formation. Okay, this is what we're forming over here. Okay, so our delta HF, okay, for magnesium chloride is negative 641.8. Okay, now we are including that negative there, okay, because it's an exothermic reaction. Okay, and so you're going to see why we use this here in a few minutes. No, it's different. Figure out the delta HF? No. We've looked at delta H. That's the big thing, that the symbols here. You've learned Q, you've learned delta H, and now we're going to look at delta HF. So these are all three different terminologies. Okay, and we're going to kind of put them all, hopefully, kind of put them all together. Okay. Okay, heats of formation. These values here have been determined for you for many substances, and they're tabulated in your book. Okay, so if you look, hopefully some of you have your books today. I meant to send an announcement to look at them, to bring your books. Okay, if you go to Appendix K, okay, if you don't have a book, try to get near somebody that does. Or share. I've got one. I won't be able to look at it, but y'all have got one y'all can look at. Got one. Looks like everybody. Okay, everybody in Appendix K? And maybe, y'all have had to get the new book, haven't you? The updated version. So it may not be the right page. Yeah. Just go to Appendix K. It's going to be at the very back. Okay. I want everybody to look. So the first column is the compound. Okay, by listing up. Okay, this portion is pretty easy once we start getting into it, but you can make simple mistakes. So you want to listen for those simple mistakes that I have seen happen. Okay, if you look at the compounds, okay, look out beside. It gives you the state of matter, gas, liquid, or it could be a solid or whatnot. Okay, be sure that you use the right value. If it's a liquid, don't accidentally use the gas form. Okay, so that's a very common mistake. Okay, so there's your compound. Now go to the first column. Okay, we're going to learn all these columns, but the very first column there, that is your delta HF. Okay, these are the heats of formation for the compounds listed. Okay, and all of these values are based on 1 mole of that substance. Okay. Okay, also look, so if you look for the heat of formation of elements that are in their most stable form, so everybody look at aluminum solid, the very first one. Okay, that's in its most stable form at standard temperature and pressure. Okay, and so its value is 0. Okay, you'll find that for bromine. So look down, bromine liquid. Okay, that one's also 0. So you'll kind of start getting used to oxygen. O2 gas is 0. Okay, so that's just the most stable form. So some of them do come up, are listed as 0. Okay, so let's look at this reaction. So we're going to keep this out, and we're going to use this really the rest of the class. Okay, so we've got hydrogen and fluorine react together to form 2 moles of HF. Okay, so if we want to calculate the heat of formation, or the standard molar enthalpy, okay, for HF, okay, we go first and look in Appendix K. Okay, so everybody look at your appendix, and you should get negative 271 kilojoules per mole. Okay, it should be roughly that. So I'll check and make sure. Okay, be sure you use in the gas phase. Okay, so negative 271. Okay. So now we're going to take that value, and this value is based off of 1 mole, right? Okay, so if you look at our equation, how many moles do we have? We have 2 for HF, right? Okay, got 2 there. Okay, so all you're going to do is take 2 times negative 271, okay, and that gives you negative 542 kilojoules. Okay, so that's the enthalpy change for the reaction using the delta HFs. Okay, if you just had 1 mole, like over here, so our magnesium chloride, we produced just 1 mole. So we just had the 1 number there. So if you look in your appendix K, that's the number, that's the heat of formation for magnesium chloride. Okay, we're going to use these heats of formation, so I want to do a quick review, which we've kind of been doing throughout. Okay, but the first thing that we learned was Q. So this is MC change of T. Okay, our units are joules and kilojoules. Okay, and then we learned about enthalpy. So that was what your whole assignment from last week was about the heat being transferred in or out of the system. And then we also looked at the moles of reaction. So we looked at that today. Okay, so here, now we have delta HF. So I just want you to get these 3 terms and be able to distinguish between all 3 of them. Okay, so this is the enthalpy for the reaction for forming it, basically. So it's the formation of whatever the substance is that you're looking at. Okay, and the delta HF values in your book are all based on 1 mole. Okay, and the units here are the same. So units are still kilojoules per mole. Okay, so this one I think came from your book. So you've got, there's a table in the chapter as well as in the end of the book. So we already kind of walked through these, but you see there's some that are 0. So like chlorine gas, carbon in the graphite form is also 0. Okay, so here's some very common values. You can use either one, but the one at the end of the book has more compounds there. Okay. Okay, Hess's law uses these heats of formation. Okay, so his law, sometimes even reading through seems complicated, but actually the mathematical part's one of the easier equations. Okay, so just bear with me. You'll get it here in a few minutes. Okay, but basically for this class and really for the rest of, we'll talk a little bit about the fact that when we look at an equation, we've got reactants and products, and we haven't really thought about what's going on in between from point A to point B. Okay, we just assume bonds break, new bonds form, we form those products. Okay, in reality, a lot goes on in between. So in organic chemistry, what we do is we start at square one and we draw out mechanisms and we go through every little step that happens between A and B. Okay, but you guys are not going to put you through that this semester. Okay, so Hess's law is saying that no matter the pathway, so from point A to point B, there may be 5 or 6 intermediates, things that are going on in between point A and point B. Okay, but no matter the pathway in which it occurs, if we add up all of the delta H's, enthalpies, for each step of the reaction, then the sum of all of these will give us our overall delta H, or enthalpy change, for the reaction. Okay, so better, the most useful form here is that if we want to find delta H, okay, so we're going back to on the board over there. Okay, this is another way for us to find delta H. Okay, we can take the sum, this is the sum, okay, the summation of all the heats of formation of the products minus all the heats of formations of the reactants. Okay, but you can't forget this A right here, these A's here are the coefficients. Okay, so you have to multiply that heat of formation value, like we just did a few minutes ago. We multiplied times 2. Okay, there was a point to that because you're going to have to do that here. Okay, so you take the coefficient and you multiply it times the value that's in your book, or I will give you on the exam. Okay, so let's look at this. So this is Hess's law in action here. We've got propane plus oxygen, and we've got a balanced equation, forms CO2 plus water. 3 moles of CO2 and 4 of water. Okay, so Hess's law says we can sum all the products and then subtract the sum of all of the reactant heat of formations. Okay, so let's walk through each step. Okay, we're looking for delta H, the overall enthalpy change for the reaction. Okay, so if we look at our products, we have 3 moles. That's all that's showing here, is that we're going to have to multiply 3 times whatever the heat of formation is for CO2. Okay, we have one more product, so we add it. Remember, it's the sum. Okay, plus 4 times whatever the heat of formation is for water. Okay, we're going to plug in those values by looking at your table. Okay, so you get this, you add your product summations together for the heat of formation minus the reactants. Okay, so you have only 1 propane molecule, so understood 1 there, and you have 5 oxygen. Okay, so we're going to multiply it times 5. Okay, so I want you all to look at your appendix. Be sure, I know it seems easy, but a lot of students make small mistakes here. And all we're doing here is plugging in the values from the appendix. Okay, so the heats of formations for these. Okay, so if you look at propane, so find it in Appendix K, okay, you should get the same value that's up there, but I want you to actually do that. Look at your appendix, see that, and see how it would be plugged in. Look at the gas form for CO2, the liquid form for water. Then your oxygen, O2 gas, is in its most stable form, so it's going to be 0 for the oxygen. Okay, and then if you look for propane, it should be negative 103.8. It's kind of in the second block on the first page, I believe. Okay, so we're looking up all the heats of formation, so how much heat has to go in or out of the system to form that product. Okay, one mistake is usually made is don't forget you're doing products minus reactants. It's going to kind of be a common expression for us. You do products minus reactants. Okay, did everybody find negative 393? Negative 285? Okay, so we're going to add these together. 3 times negative 393 plus 4 times negative 285. Get your number there. And then we're going to subtract the reactants. So did everybody see negative 103? Okay, for propane. Okay. And then 0 for oxygen. Okay. So we just subtract that out, and we end up with a negative sign. Okay, so this sets us up to tell us whether the reaction was exothermic or endothermic. So whatever sign you get here tells you exo or endo. Okay. So we have negative. If we were to look at the reverse reaction, okay, we're going to do that later in the semester, but say we looked at it this way, okay, then we would get an endothermic reaction. We'd just get a positive sign there. We get the same value. Okay, any questions on this? I want you to start practicing. These are on your sheets as well, so I don't know how much time. Maybe we can practice some on Monday if we don't have time today. This is the most useful way to use Hess's law, because most times, because of this appendix, all these are tabulated for us. We can just plug the numbers in and get what we expect to be our delta H for an experiment. However, there is one more use but not as common. Okay, and this basically is just more or less just algebra. Okay, so we're going to be given the delta H of the reaction, and we're going to try to find the delta H formation of one of the reactants or products. Okay, so if you look here, I'm going to kind of get you started, and then I want you to actually work it out. It's mostly worked out here, but I want you to actually do this, on your paper. But really, like I said, it's mainly algebra. Okay, so this time we're given delta H. Okay, so if we think about our setup here, now delta H we know, right? So it's going to plug in right here. It's negative 1,124. Okay, then we take products minus reactants. Okay, well what we're looking for is SH2, this reactant right here. So that's like our X in an algebra problem. Okay, so we have products, so we look these up, so I actually gave you these values. So you would find, this is more like what I'll do on an exam. Instead of printing out the whole appendix, I'll give you the values underneath the compounds. Okay, so we take our products, 2 times that number SO2 there. Okay, we also have 2 of our water molecules. Okay, so we take products, the sum of those, minus the reactants. Okay, so this time we have 2. Okay, we can't forget that 2 from the equation. But this is like our X. So if you didn't want to put in delta HF there, you could just put 2X if you wanted to. Plus 0. So pretty much not even worried about this portion. Okay, because oxygen we know has a heat of formation of 0. Okay, so now all you got to do is solve for X. Okay, so you have negative 2 here. It kind of goes through and shows you, okay, but I want you to actually do this on your paper. Get your numbers, be sure this is correct, and you get it to match up. Okay, be sure you're bringing your calculators to class. We're going to be using them. See if I need to borrow mine. All you're really doing is isolating your variable, and then you've got to get rid of that 2 that's out front. But you can move to whichever side you want to move to isolate everything. how I did it, I would add the 1165 to the left side of the equal sign. Okay. Everybody does algebra differently. You guys probably know more tricks and things than I do, but this is how I would do it. If you wanted to move this to this side and that here, however you want to do it is fine by me. Okay, and then we have to get rid of that 2 because we just want to solve for x. We're not looking for 2 moles of SH2. We're looking for 1 because our heat of formation is based on 1 mole. So we divide by that -2. So we are set with our negative sign here. So that means it's an exothermic heat of formation value. So the heat is released. We should get 20.6 kilojoules. Okay, if you've got that homework sheet, go ahead and pull it out. And I'm going to pull it up from Blackboard and just kind of walk you through it, kind of get you started on it if you haven't already. Still don't have a browser key. Okay, so here's your worksheet, or homework number 1. Okay. These are 1, 2, and 3 are all calorimetry problems. Okay, so that would be everything we covered up through last Wednesday. Okay, and you've got to be real careful with what it's asking you for. So be sure. So this right here is asking for how much heat was absorbed by just the calorimeter. Okay, so you may not have to do all of the steps. Okay, you've got to think about what you're being asked there. Okay, number 4, let's see, 4, 5, 6, and 7. Okay, that's what we did in the beginning of class. So we took our grams, converted to moles, went to moles of reaction, and then we use our heat value. Okay, so that was from the first part of class today. Okay, then when we get down, okay, number 7 is probably the hardest one, so we may go over it either today or Monday. Okay. Okay, and then 8 and 9, what do these look like? What do you think you'll use for these? What law? Hess's law, right? So these HFs right here, whenever you see those heats of formation, we're going to automatically think of Hess's law because it tells us we can find delta H for the reaction by adding up the sum of products minus reactants of all the heats of formation. So I actually give you these values here. Okay, and why I have multiple choice here, don't really need it, but just kind of, if you don't get a value that looks anything like any of those answers, then you've done something wrong. So we can go and try to figure it out. Okay, number 10 is actually really easy, but we haven't covered delta E yet, so we'll do that on Monday. Also, if you look up at number 1, okay, you have a positive and a negative value. Okay, you can kind of just X this one out. It doesn't, I'll accept both. It's wanting you to show, it's saying heat absorbed, so technically it should be positive because something is absorbing the heat. You can't have negative. Okay, but that is confusing to some students because it's exothermic, so why couldn't it be negative there to show it's exothermic? So actually I'm giving you the answer. It's A. So if you don't have this printed, you need to be sure. If you do have it, we've just got a few minutes to work on it. I'll leave these up here. Okay, for those of you that don't, you need to be sure you have it or have it written out or whatever, because we'll be going over some of these, and there's no sense in not getting some of your homework done while we're in class. So. Probably. Okay, I'll leave these up here, and you can ask questions or work on them for the last few minutes.